90 kilometers beneath your feet, something just happened that physics said was impossible, not theoretically rare, not very unlikely, impossible. At that depth, the pressure is so massive, the heat so extreme, that rock isn't supposed to behave like rock anymore. It's supposed to bend, flow, melt, like thick honey, not solid stone. Rocks that flow don't snap, and rocks that don't snap can't cause earthquakes. That was the rule. For decades, that was the law of physics every seismologist trusted, until scientists went back and confirmed something that shouldn't exist: an earthquake, deep beneath a continent, at a depth where the rules say it simply cannot happen. And once you understand how this is even possible, you'll never think about the ground beneath you the same way again. Okay, let's start with what you probably learned in school. Earthquakes happen when two pieces of Earth's crust, called tectonic plates, grind against each other, build up pressure, and suddenly slip. That sudden slip sends shockwaves through the ground, and that's the shaking you feel. Makes sense. And for shallow earthquakes, the kind that happen near the surface, where most major quakes occur, that explanation is completely correct. But here's the crack in that knowledge. That mechanism only works because surface rock is cold, rigid, and brittle. It can crack, like a dinner plate dropped on tile. The deeper you go into Earth, the hotter and more pressurized everything becomes. By the time you're 90 kilometers down, the rock should be acting completely differently: soft, plastic, flowing under pressure instead of cracking. Geologists call this the brittle-ductile transition, and it's supposed to be a hard limit. Below it, earthquakes, real, sudden, crust-cracking earthquakes, shouldn't be physically possible. So here are the questions we're going to answer today. How can rock crack at a depth where it should only bend? What did scientists discover that broke this fundamental rule? And what does this mean for the cities sitting on top of fault lines you've never even heard of? So let's go deeper than anyone has ever taken you before. Literally. Let's build the foundation first. Literally. Near Earth's surface, the crust is made of huge, rigid slabs called tectonic plates. They're constantly moving, incredibly slowly, just a few centimeters a year, about as fast as your fingernails grow. But these plates don't slide smoothly. They catch on each other. Friction locks them in place, while the forces driving them forward keep building and building, like stretching a rubber band tighter and tighter. Eventually, the stress becomes too much. The rock breaks. The plates lurch suddenly into a new position. And that sudden, violent movement sends seismic waves rippling outward in every direction. That's the earthquake you feel. This is called brittle failure. Solid, cold rock cracking under stress, just like a dropped ceramic plate. Now here's where it gets strange. As you go deeper into Earth, two things increase dramatically: temperature and pressure. By 90 kilometers down, temperatures can exceed 1,300 degrees Fahrenheit, and the pressure is roughly 30,000 times what you feel at sea level. Under those conditions, rock stops behaving like a brittle plate. It starts behaving more like thick caramel, able to slowly flow and deform without snapping. Engineers and geologists call this ductile behavior. And here's the key principle. Ductile materials don't crack suddenly. They stretch, they bend, they flow. No sudden crack means no sudden release of energy. No sudden release of energy means, according to the textbook, no earthquake. This boundary, where rock transitions from brittle, crackable material to soft, flowing material, is called the brittle-ductile transition zone. For decades, scientists treated it like a hard ceiling. Earthquakes happen above it, never below it. But here's the part that nobody talks about. In 1979, seismic instruments in Utah picked up a deep tremor that didn't fit the rules. And for decades, it sat in the data, unexplained, mostly ignored. Modern researchers went back through decades-old seismic records using far more advanced analysis tools than existed in 1979, and they confirmed it. That signal wasn't noise, it wasn't an error, it was a real earthquake, roughly 90 kilometers beneath the surface of the continental United States, deep inside the supposedly earthquake-proof ductile zone. Did you know? Scientists have a name for this category of mystery: intermediate depth earthquakes. They occur in a zone where the physics textbook says they shouldn't be able to happen at all, and researchers have spent decades trying to figure out the missing mechanism. Coming up, the secret process that might explain how solid rock can still snap, even when it should be flowing like syrup. In every geology classroom, the brittle-ductile transition is taught as a clean line. Above it, earthquakes. Below it, smooth, silent flowing rock. Simple, predictable, wrong, or at least incomplete. Geophysicists who study deep earthquakes know something most textbooks gloss over. There isn't just one way for rock to suddenly fail. One leading theory is called dehydration embrittlement. Deep rock can contain water locked inside mineral structures. Under extreme heat and pressure, that water gets violently squeezed out, and for a brief moment, it creates a pocket of high-pressure fluid that weakens the surrounding rock and lets it fracture suddenly, even though the rock around it should be flowing instead of cracking. Think of it like a tightly packed sponge suddenly releasing trapped water under pressure. The surrounding structure briefly collapses before stabilizing again. Another theory involves something called thermal runaway shear. Friction along a tiny weak zone generates heat faster than it can dissipate, softening the rock locally just enough to let it slip catastrophically, like ice suddenly melting under a skate blade. Neither theory fully explains every deep earthquake. Scientists are still piecing it together. That uncertainty itself is the hidden truth. We are still discovering how the planet beneath us actually behaves. Wait, it gets even more interesting. Deep intermediate earthquakes aren't just a Utah curiosity. They've been documented beneath subduction zones around the Pacific Ring of Fire, Japan, Chile, Indonesia, places where one tectonic plate dives beneath another, dragging cold, brittle rock down into the hot ductile zone before it has time to fully heat through. That cold rock, briefly trapped at depths where it shouldn't still be brittle, can crack, generating earthquakes far deeper than the simple textbook model allows. The Utah case matters because it proved this isn't as subduction zones at ocean trenches. It can happen deep beneath a stable continental interior, somewhere geologists assumed was about as seismically boring as it gets. Here's the most shocking fact in this entire video. There are deep earthquake zones scattered across the planet that scientists still cannot fully explain, meaning the rulebook for how the ground beneath entire continents can fail is still being rewritten right now in 2026. You've probably noticed that earthquake warnings and building codes always focus on shallow, well-understood fault lines. California's San Andreas, for example. That's not an accident. Engineers design for the threats they understand best. But if deep, hard-to-predict earthquakes can occur in places once considered geologically quiet, that changes how seismic risk needs to be calculated for infrastructure built far from obvious fault zones. Next time you cross a bridge or walk into a tall building in a region you assumed was earthquake safe, know this: engineers are increasingly factoring in deep, less understood seismic sources, not just the fault lines you've heard of on the news. This is exactly why the U.S. Geological Survey has spent years expanding seismic sensor networks across the country, including regions far from California, specifically to catch deep, unusual earthquake activity that older, sparser sensor networks would have completely missed. Modern seismology increasingly relies on dense sensor arrays and machine learning pattern recognition to catch these subtle deep signals, the same kind of signal that sat misunderstood in 1979 data for decades before modern tools could properly interpret it. This same principle, material failing suddenly under conditions where it should be flexing instead of cracking, is the exact same engineering concern behind metal fatigue failure in aircraft wings and bridge cables. Materials engineers spend entire careers studying why solid materials sometimes fail in ways that violate their expected behavior under stress. And this is just the beginning of how deep this goes. Now here's something that most people never connect to this topic. Deep earthquakes don't something stop at 90 kilometers, Scientists have confirmed earthquakes occurring as deep as 700 kilometers below the surface, in a completely different zone called the transition zone, where pressure is so extreme that minerals physically rearrange their crystal structure. At that depth, a different mechanism is suspected: sudden mineral phase transitions, where a mineral's crystal structure abruptly collapses into a denser form, releasing energy, almost like a tiny implosion deep inside the planet. Think of it like ice suddenly transforming into a denser form of ice under extreme pressure. The structure doesn't melt or flow, it collapses and rearranges almost instantly, releasing a burst of energy in the process. Deep inside Earth, minerals may be doing something similar, snapping into denser crystal structures so fast that it sends shockwaves through solid rock that should be too hot and pressurized to ever crack. We are still mapping the deepest mechanics of our own planet in 2026. So here's what we uncovered today. Deep earthquakes happen in a zone where rock should be flowing, not cracking, and scientists still don't fully agree on the exact mechanism that makes it possible. The Utah earthquake, confirmed nearly 90 kilometers underground, proved this isn't limited to ocean trench subduction zones. It can happen beneath stable continental interiors too, and earthquakes have been confirmed as deep as 700 kilometers, driven by entirely different physics involving sudden mineral transformations deep inside the planet. The ground beneath your feet isn't the simple, well-understood system you were taught in school. It's an active area of scientific discovery, and the rules are still being rewritten by researchers analyzing data that sat unexplained for decades. Now I want to know, did you know earthquakes could happen this deep underground? And do you live near a fault line you didn't even know existed? Drop it in the comments. I read every single one. In our next video, we're going somewhere even most engineers haven't fully thought about. We're going to find out why a new generation of solar panels just shattered an efficiency ceiling scientists thought was physically permanent. The world is not what it looks like on the surface. It never was. This is Logivra, and the logic was always there. You just needed someone to show you where to look.